So, good evening, everyone. Welcome to the NPTEL online certification course. And today we are going to solve some problems regarding the wastewater treatment and recycling. And we are in week 7 now. So, we will quickly go through like what are all the topics that has been discussed in week 7. I hope I am audible. So in week 7 we started looking at the anaerobic treatment of wastewater, like what are the basic concepts related to that, and also we compared the aerobic and the anaerobic system, that was advantages and the disadvantages, and then we moved into the anaerobic degradation processes where we learned the various processes related to anaerobic digestion, starting from the hydrolysis, acetogenesis, and methanogenesis, and at last we saw the COD balance. And then we learned about some characteristics and applications of the anaerobic degradations, such as the factors affecting the processes and also the various different types of systems and classifications. And then we moved on to learning about the USB reactor, that is the upflow anaerobic slash blanket reactor. We saw the working principle, design criteria, advantages, disadvantage, and the applicability part. And after that, we learned about some more high rate and low rate anaerobic processes. So this was the whole uh, basis of our week 7 classes. So I have some subjective and objective questions. So we will go through each of them one by one. Okay. So starting with the subjective question. So this is the first question which I have. So it says that develop the theoretical mass and volumetric conversion factors of COD to methane at the standard temperature and pressure conditions, that is 0 degree Celsius and 1 atmosphere. So using the ideal gas law. So here we have to develop a relationship between the methane generated per kg or per unit of COD. So we have learned in anaerobic process that methane is being produced. So here we have to, like, we can find out or develop a relation between them based on the COD. So if you have noted down the question, so here we are talking about like if methane is being oxidized, so per gram of methane how much oxygen is required? What is the COD content? Okay, so we will see how to solve this problem. Okay, so the basic reaction for a balanced reaction for COD as oxygen from methane. So I will write. So this is the basic reaction. Okay, so we know the total mass of any methane is 16, whereas 2O2 will be 2 into 32. So we can see the theoretical mass conversion factor, which will be 16 gram per mole as CH4 divided by 2 into 32 gram per mole COD as O2. So this will be equal to 0.25 grams CH4 per gram of COD. So we are taking COD as O2, so it will be 0.25 gram of CH4 per gram of COD. So we can say 1 kg COD is equivalent to 0.25 kg CH4. Right. So what will be my number of moles of methane? So my NCH4 value will be 0.25 gram CH4 plus per gram of COD divided by 16 gram per mole as CH4. So I will change gram and kilogram. So it will be 15.6 mole CH4 per kg COD. So per 1 kg of COD we can get 15.6 mole of CH4. So this is the basic, like we found out the number of moles of methane, right? So now we have to derive the equation as per the ideal gas law. So we know that by ideal gas law, the total volume can be equal to number of moles into the molar volume of gas at STP. Okay, or the total volume can also be found out from PV is equal to nRT. It's a universal gas law equation. So we can also use, so it will be equal to nRT by P. So by both of these equations, we can find out the volume of gas. So here V denotes the volume of gas occupied at a particular temperature and pressure. It is in liters. Okay. N is the amount of gas which is in moles. Vm is the molar volume of gas at STP, and it is generally 22.4 liter per mole. So molar volume of gas at STP will be always equal to 22.4 liter per mole, and R is the universal gas constant. So it is generally taken as 0.082056, and the unit is liter atmosphere per mole Kelvin. And T is the average gas temperature in Kelvin, and P is the absolute pressure of gas in terms of atmosphere. Okay. So this was all about the ideal gas law. Now we will try to put the values in it and find the answer. So by the first equation, we can get the volume of CH4 as moles of CH4 into the molar volume. So it will be 15.6. We have found out before, 15.6 mole CH4 per kg COD into 22.4 liter per gram mole. So it will be equal to 350 liter CH4 per kg COD. And similarly, from the second equation, we can also find the volume of CH4, which will be equal to NCH4 into RT by P. So it will be again equal to 15.6 mole CH4 per kg COD into R is 0.082056 into 273, because 0 degree Celsius is equal to 273 Kelvin, divided by 1 atmosphere. So it will also turn out to be 350 liter CH4 per kg COD. So therefore we can say that 1 kg of COD produces 0.35. I have changed liter into meter cube. So 0.35 meter cube CH4 per kg CO2. So This is all we have to derive the relation for. So for 1 kg of COD, it produces 0.35 meter cube CH4 per kg COD. Okay, I hope this was a simple relationship. So if we see, for a quick recap, first we found out the balance reaction, then we found out the theoretical mass conversion factor, and we found the number of moles of methane. And then we just applied the ideal gas law equations and find out the volume, and we found out it to be 350 liters CH4 per kg CO2. Is it fine? I hope it is fine for everyone. Okay. So this was the first question. Latecomers, those who have joined a bit late to the class, uh, you can see this question, and also you can access my YouTube class again uh, in my YouTube channel. Okay, so no need to worry about that. So we will now go to the next question. Okay, so the next question says, an anaerobic treatment facility receives industrial waste. The wastewater flow is 800 meter cube per day, and the total COD, both soluble and particulate, is around 2500 milligram per liter. So you have to calculate the volume of the methane produced and also the total volume of biogas. So both we have to find out. So the extra information given is 80% of waste is degraded, because we know that in any anaerobic treatment facility we don't get full 100%, or some part of COD is still left. So it says that 80% of waste is degraded, and the methane content of the biogas is 64%. And here also the M value, that is the methane conversion factor, is given as 0.35 meter cube of CH4 per kg of CO2. So this is the question. It's a two-step question only, very simple. So we have the flow rate value, we have the COD value, we know how much is getting converted, and also the methane conversion factor per gram of CO2. Okay. So I hope you have taken a screenshot or note down the question. Okay. So this is question number 2. So we have been given the flow rate as 800 meter cube per day. Okay. And the COD value as, 2500 milligram per liter, and E value, that is how much has been degraded, is zero point 0.8. 80% is given. 80% of the is given, and M value is 0.35 meter cube CH4 per kg COD. Okay, so these are all the data given to us. So first we will find out the volume of CH4, volume of methane. So here we are finding the volume of methane per day. So volume per day is nothing but the flow of CH4. So QCH4 we will find out, which will be equal to Q E into the COD value into M. Okay, so it is 800 meter cube per day into zero point 0.8 into 2500 kg COD per meter cube. I have just changed milligram per liter into gram per meter cube into 0.35 meter cube CH4 per kg COD. So, and also we will have another conversion factor from gram to kilogram. So this is the total CH4 volume per day, which is the flow of. So we will get it as 560 meter cube per day. If it has been only meter cube, then we would have said volume of CH4. But here it is the flow of CH4, that is 560 meter cube per day. Okay, so this was pretty direct. We just multiplied the flow rate into how much factor is degrading, the total CO2 content, and per grams COD, what is the methane generation. So by multiplying all, we got it as 560 meter cube per day. And next, we have to find out the total biogas content. So in the question, it says that the methane percentage is 64. So with the help of that, we will find the flow rate of biogas. That will be QCH4 divided by 64% because it is given as 64 into 100%. So it will be equal to 560, 64 into 100. So it will be equal to 875 meter cube per day. So we can see that the biogas that is totally generated is 875, out of which our methane content is 560 meter cube. So everything it is in terms of meter cube per day. Okay, it was a very simple question, direct application of whatever we performed in the question one. So this is the answer for question number. Okay, so those who have joined late, please see this question. We have just discussed how to solve this question. The answers are 560 and 875 meter cube per day. Okay, so shall I move to the next question? Is it fine?
Okay, sir.
Okay. Others are okay. You can react. Just give a reaction. Okay, fine.
Yes, sir.
Yes,
Okay.
okay, sir.
Okay. Thank you. Thank you. Okay. The next question. It looks a bigger question, but it is also a very simple question. So an anaerobic reactor receives an average mass COD loading of 1500 kg COD per day. So COD value is given from a local food processing plant. Calculate the volume of methane generated daily if efficiency of waste utilization is 80%. Again, that degradation factor is also given. Also estimate the amount of energy contained in methane. So here with the volume of methane, we have to also find the amount of energy that is contained in methane. And the biomass yield is given as y is equal to 0.08 gram VSS per gram COD. And again, KD value is 0.03 per day. The average reaction period is 10 days. And the CH4 conversion value per gram per kg of COD, that is 0.35. So everything. So it is given in terms of meter cube per kg COD at STP. Okay, please go through the question again. Take a screenshot. Abdul, you want to say something?
No, sir. No, by mistake it is.
Yeah, please. Okay, so here we have to find the how much biomass is being produced in the reactor. So with the help of this biomass value only, we can find out the quantities. Okay, so we will solve the question. So in last question, we saw that much of the part of all the part of the COD was getting converted into methane. But we know that in actual case that is not the reality. Some part of COD will be utilized to form biomass. So here the details regarding the biomass conversion has also been given. So first we have to find out the net biomass produced in the reactor. Okay, so if we if you see the net biomass reactor, that is px value, that is first we have to find the y observed value as I told you before. So the total yield value is given. If we divide it by 1 plus kd theta c, we will get the y observed value into e, that is the conversion factor, into the s naught, that is my COD value. So here e value is zero point 0.8, S naught value is 1500, and KD value is given as 0.03, and theta C I will take it as theta because my mean cell residence time and HRT I am considering it to be same, so that is given as 10 days. So these are all the values. I will just simply substitute it. 0.08 divided by 1 plus 0.03 into 10 into zero point 0.8 into 1500. So this will become as 74 kg VSS per day. So with the information which has been given to us, we found out that the net biomass produced in the reactor is 74. So some part of COD is being converted into biomass. So now when we will find out the volume of methane, we will simply subtract it from the earlier value. So So that will be equal to m into E naught E into S naught minus the total value. So 1.42 into Px, because some part is being utilized. So we know that it is 0.35. E value is zero point 0.8 into 1500 minus 1.42 into 74. So we will get it as 383 meter cube of CH4 per day. So here we have seen, because some part of COD is being utilized for biomass, so we are just simply subtracting it from the total COD content that is being converted into methane. So 1.42 was the conversion factor, if you know, to in terms of oxygen requirement. So I have just subtracted it from that. So this is the total methane generated per day. And if you see the energy content, so for energy content, we should know this value. This is not given in the question, but in general, we should know the energy content of CH4. It is equal to 39,700 kilojoule per meter cube. So per meter cube of methane, we can get 39,700 kilojoule of energy. So if we find the total energy of methane, that will be 383 meter cube CH4 per day into 39,700 kilojoule per meter cube of CH4. So it will come as 1.52 into 10 to the power 6 kilojoule per day. So this is the total energy content in the methane which we have produced per day. Okay. So any problem with this question? Any conceptual problem that you are not able to understand? So the difference between the previous problem and this problem is, in previous problem we considered that there is no biomass produced, so we were not subtracting it. But in this question, the details regarding biomass have been given, so we have to consider that part and we have to subtract it from the total COD value. So this is the basic difference between both the questions. So we know when to use which formula. Okay, so I hope it's clear to all of you. So simple problems, just little bit, uh, just a,
So this energy content of CH4, this 39,700, that is a constant value or it may vary?
no, no,
That is a constant.
it's a constant value. Most more or less, it's a constant value.
Okay, sir.
So it should be given in the question, but since it was not given in the question, I have written it down. So mostly some energy content tables will be there for CH4, CO2, hydrogen, everything. So from there I have taken. Okay, so more, but mostly it will be given in the question. Okay, so this was the question. We got the answer as 383 meter cube of CH4 per day and 15.2 liters per 6. Or rather 1.5, sorry, it's 15.2 liters per 6. Anyway, you can check the calculation once again. So this was the problem. Okay, so this is the next problem and the final subjective problem. So an organic waste is undergoing anaerobic decomposition. The chemical formula is the waste on dry weight basis is C50 H100 O40N. The dry weight of the organic waste decomposed in the reactor is 500 kg per day. Assume that the weight of biomass produced is ignorable. So here they are telling that there is no biomass conversion. Calculate the total mass and volume of biogas produced and the mass and volumetric ratios of CH4 to CO2. So we have a waste whose chemical formula has been given. So we have to find out the if it is getting converted in anaerobic decomposition. So how much of methane, carbon dioxide, ammonia will get produced. So we will see one by one how we have to go through this problem because here the formula of the compound is given. So it makes the work very easy. So this is question number 4. So if you see the general formula of conversion of any uh, compound into CH4, CO2 and NH3 in terms of ABCD, we can write it as CaHbOc Nd plus 1 by 4 4a minus b minus 2c plus 3d H2O. It will give 1 by 8 4a plus b minus 2c minus 3d CH4 plus it will give 1 by 8 4a minus b plus 2c plus 3d CO2 plus DNH3. So this is the basic formula. So here we have the compound as C50H100O40N. So this will imply as A is 50, B is 100, C is 40 and D is 1. So we have to simply substitute this formula in this reaction, these values in this reaction. So if we substitute these values in this reaction, so ultimately we will get it as C50H100O40N plus 5.75 H2O will give us 27.125 CH4 plus 22.875 CO2 plus NH3. So you can check the calculations later. I've just given you the balanced equation from the values of ABCD. So the total molecular mass of this will be around will be 1354. For this it will be 103.5. For this it will be 434. For this it will be 1006.5 and this will be 70. Okay. So we got the molecular weight of everything. So now we will see the total weights of every gas that we have produced. So we know that the total dry weight is 500 kg per day. So here 1 mole of this compound produces 27.125 moles of CH4, or rather 434 gram of CH4. So with that logic, we will find each and every uh, gas volume, gas weight per day. So my weight of CH4 will be equal to 434 divided by the 1354, that is per molecular weight of the organic waste given, into 500 kg per day. So this will turn out to be 160 kg CH4 per day. Similarly, weight of CO2 will be 1006.5 by 1354 into 500. It will be 372, and NH3 will be 17 by 1354 into 500. It will be 6.3. Okay, so this is kg CO2 per day. This is kg NH3 per day. And if we find the moles, so moles of CH4 will be equal to 160 kg divided by 16. The molecular weight of methane is 16, into 1000. We are changing it to moles. So it will be 10,000 moles per day. And CO2 will be equal to 372 into 10 short 3 divided by CO2 is 44. So it will be 8450 moles per day, and NH3 will be equal to 6.3 into 10 to power 3 divided by 17. It will be equal to 371 mole NH3 per day. So in that way, we have found out the weights and the moles of each of the gases produced. It is just calculation, simple calculation. And now, once we found the moles, we can find the volume. So as I have told you before, the volume of any gas will be equal to the moles into the molar volume. So moles, we know it as 10,000, and molar volume of any gas is 22.7 liter per mole. I will change the liter into meter cube, so it will be per mole. So it will turn out to be 224 meter cube CH4 per day. So in the same value, in the same way, I can find out the volume of CO2, which will be 189 meter cube of CO2 per day, and VNH3 will be equal to 8.3 meter cube NH3 per day. So with the help of this equation, I can find the weight of all the gases. Very simple and straightforward. So now the total mass of my biogas. So in the biogas, we generally consider the CH4 part plus the CO2 part. So it will be 160 plus 372. That is 532 kg of biogas per day, and total volume of biogas, again VCH4 plus VCO2, it will be 224 plus 189 equal to 413 meter cube of biogas per day. So we have found out the all mass, volume, everything related to the gases produced. So if you see the proportion, by mass also we can do, by volume also we can do. I will do the volumetric ratio. We can try out the mass ratio also. So if we see the volumetric ratio, so CH4 will be 24 out of total 413. So it will be around 54%, and CO2 189 out of 413, so it will be around 46%. So this is the volumetric ratio. So the my volumetric ratio of CH4 over CO2 will be 224 divided by 189, that is 1 1. So this is my volumetric ratio. Very simple. So just with the help of this basic equation, we can find the weight, volume, everything. If the ultimate analysis of the organic waste is done and we know the subscript of all the carbon, hydrogen, oxygen, and nitrogen. So by the help of ultimate analysis, we find the various carbon, nitrogen, or oxygen contents of the organic waste. Is it clear? I hope it is clear. Today's questions are very simple because there is nothing much in this. So these were all the questions that I had for subjective. So we got 532 kg of biogas per day and 413 meter cube biogas per day. Okay. Okay. So now we'll discuss some MCQ problems. We will quickly go through them because those are very easy. We can just answer it if you know. So the first question is the primary constituents of biogas typically produced during anaerobic treatment of wastewater are. So it is talking about biogas. What is the primary constituent? So which of the option is correct?
This question answer is C, 70% methane and 30% carbon dioxide.
Yes. So mostly our methane concentration is very high with respect to carbon dioxide. So most of the organic carbon is converted into 70% of methane and 30% of carbon dioxide. There are other gases also like hydrogen, ammonia, but the volume is very less. Okay. So the next question: which of the following is likely to be a major disadvantage of anaerobic wastewater treatment process as compared to the aerobic? So we are comparing both anaerobic and aerobic. So which of the following is a disadvantage? A, lower removal of nutrients. B, higher land requirement. C, lower functionality under high organic load. And D, all of the above.
Which is answer A, lower removal of nutrient and pathogens.
Okay. Anybody else?
Answer A.
Answer A. Yes. So in anaerobic system, we know that the nutrient removal and the pathogen removal is not very high, or rather, it is in the lower side only. So option A is the correct answer. So these are the basic drawbacks of any anaerobic system. So after any anaerobic system, what we do, we provide a polishing treatment so that or any tertiary kind of treatment so that it will help in removing the nitrogen phosphorus content and also the pathogens from the system. Okay, so here we are talking about the various anaerobic processes. So we have to arrange them in correct order. So please see the first and the second list. Try to recall all the processes that we have learned in anaerobic system and tell me the correct answer.
Option D.
Option D. So you are saying that first hydrolysis, then acidogenesis, then acetogenesis, and then the methanogenesis. Yes, this is the correct answer. So can someone tell me what is the rate limiting step? in the anaerobic digestion process. Rate limiting means which takes more time or governs the kinetics of the system. Which is the most difficult process or the late limiting process primarily in any anaerobic digestion. Are you understanding my problem? I am asking about the rate limiting process. Okay, so I will tell you hydrolysis is the rate limiting. Majorly hydrolysis is the main limiting. Sometimes methanogenesis can also be the case, but primarily hydrolysis is the rate limiting process. Okay. Okay. So the next question. In an anaerobic degradation, the formation of acetic acid typically occurs in which of the phase? Very simple and direct question. So in which of the following process acetic acid is being produced?
Is it B, acetogens?
It is B, acetogenesis. Acetogenesis is the process in which the products which are formed in acetogenesis, that is the volatile fatty acids, it is being converted into acetates and hydrogen. So it is the acetogenesis process. So next question, the components of COD are that are not typically removed by anaerobic degradation. So in anaerobic degradation, we know the various contents of COD, soluble, particulate contents are being removed. So which of the following is not removed in a COD? In anaerobic digestion, which of the following COD part is not removed?
Option B.
Option B, yes, the recalcitrant COD. So the biodegradable and the particulate matter will be easily removed in the anaerobic degradation, but the recalcitrant COD will not be removed, which is persistent, which doesn't leave the system. So will not be removed. Okay, the next one. Typically, the least toxic volatile fatty acid is. So there are
It is B, acetic acid.
acetic
Acetic
acid,
acid. Yeah.
acetic acid. Okay, so it is right that acetic acid is the least toxic volatile fatty acid, and we have just seen that in the that acetate is formed in the last stage, that is not the last stage before the conversion to methane. It is the one of the last VFS that is being produced. From that, the next methane is being generated. So acetic acid is the least toxic volatile fatty acid. Okay, so the next question says an increase in ammonia concentration causes rapid production of volatile fatty acids during anaerobic degradation. These VFAs cause a decrease in pH in the anaerobic reactor, leading to reduction in the methanogenic activity. So there are two statements A and B. We have to tell whether both are true and whether one is the other explanation or one of them is false. So which is the correct option? A, B, C, D. So it is saying that due to more ammonia, more VFAs will be generated. And then in the next question, it is saying that due to more VFAs, which are basically acids, there will be a decrease in the pH. Because of that, the methanogenic activity will be getting inhibited. So these are the two statements. You have to find out whether both are true, both are false, one is true, one is false, or one is the explanation for the other. Okay, Abdul is saying that B statement is false. So Abdul, if B is false, how would you correct the statement B?
No, actually, I choose C. A
Okay,
is
okay,
A,
A is
A is true, B is false.
okay. If okay, you are telling that B is false, then what is the correct answer? What is the correct statement rather? What is the correct statement?
And an increase in ammonia concentration causes rapid production of volatile fatty acids.
That is
Uh,
true. That is true.
yeah,
But what about statement B?
that is false.
Actually, B is also true. See, because when there is an increased ammonia concentration, it would lead to more VFAs, that are volatile fatty acids. So whenever acids are being produced in the system, more and more acids are produced in the
Mm.
system pH will go down. So
Okay,
once
okay.
the system pH will go down, the methanogens will not be very much active. They are not able to survive at very low pHs, and they are
Yeah,
not
yeah.
able to convert these VFAs into methane. So that's why
Okay.
the methanogenic activity will get reduced. So both the statements are
Both,
true.
both, yeah, both
Both the
statement is
statements are true, and
yeah.
also A is the correct explanation for B. So it is
Okay, sir.
also related. It is sequential. So
Mm.
both is correct. Okay.
Okay, sir.
Okay, fine. Okay, so the next question. Upflow anaerobic sludge blanket reactor is an appropriate example of. So upflow, upflow anaerobic sludge blanket reactor is an example of. Is it a high rate with suspended growth, high rate with attached growth, fixed flame anaerobic reactor, or low rate anaerobic filter?
Option A.
Option A, okay. So option A is correct because in upflow anaerobic sludge blanket reactor, the biomass is in suspension. So there is a suspended growth. So option A is correct. Okay. So the next question is the biochemical reactions in USB reactor majorly occur in. So where does the biochemical reactions happen in a USB? That is the upflow anaerobic sludge blanket reactor. Where does the biochemical reactions happen? A, is it in GLSS? B, clarifier zone? C, sludge blanket zone? Or D, settling zone? Please tell me the answer. Settling zone. Settling zone. Why settling? Why do you think it's a settling zone? What is GLSS? Can someone tell me the full form of GLSS? That is gas, liquid, and solid separator. So in GLSS, the gas, liquid, solid separation is done. In clarifier zone, all the biomass will get clarified, it will get settled. In settling zone, the actual settling of biomass is happening. But whereas in the sludge blanket zone, where my sludge is being produced, it holds all the biomass for the reaction. So in the sludge blanket zone, or which is called as the reaction zone, it holds the granular biomass, and without the biomass, there will be no biochemical reactions. Okay, so the correct answer is sludge blanket zone, not the settling zone. Settling zone means it has already settled.
Sir, this is coming somewhere middle of the
Yes,
reactor. Is it?
yes, yes.
Okay.
Okay. So identify the incorrect statement concerning the anaerobic treatment. So four statements are given. You have to find the incorrect one. Heavy metals and sulfides may act as a potential inhibitor. A lesser return requirement is a primary advantage. A major drawback is the probable production of foul odor, and the organic carbon is entirely converted to sludge.
Option D.
Option D. Yes, because the entire carbon, organic carbon, is not converted only to sludge. It will be some will be degraded into the various gases that are being produced. Some will just leave the system as it is, and some will be converted into sludge. So D is the correct option. Okay. Adequate mixing in USB reactor is facilitated by. So what out of these four options helps in the adequate mixing? A. Filtration effect. B. Upflow enzyme and gas bubble formation. The GLSS zone, or all of the above.
All the above.
All of the above. Okay. So is the GLSS zone also?
Upflow, resume, and gas ball formation.
Yes. See, GLSS zone means gas, liquid, solid separated. So there everything is getting separated. There will be no mixing in that. And also not the filtration effect, but only the upflow regime and the gas bubble formation. It will help in adequate mixing of the USB reactor. Okay, not all of them.
Okay, okay. Thank you, sir.
The next question. An anaerobic reactor that requires inert media for operation is, which of the following is an anaerobic reactor which requires a media also? So A, anaerobic contact process, anaerobic filter, anaerobic fixed film reactor, or all of the above. Which ones required an inert media for its operation? We have seen various types of anaerobic reactors. So which of these required a inert media? Actually, the answer is all of the above, because in all of them it requires an inert media. Okay, so if in the anaerobic contact process also there should be a contact with the media, and in the filter also, and also in the fixed film reactor also. So everything requires an inert media. So these were all the MCQ problems that I had. So if you have any other questions, you can ask me now regarding all the questions that we discussed, all the subjective problems and then the MCQ problems. We solved four subjective problems. So so those who have joined late, they can access all the subjective problems from my YouTube channel, and then we discuss some MCQ problems. So the video will be uploaded. You can refer to that. And if you have any queries regarding these questions right now, you can ask me. Hel-
Sir, this question,
Okay. Yeah, this was the homework question last time which I gave.
yes, sir.
Did you try to solve this question?
Yes, sir.
Okay. What did you get the answer as?
I did not get any answer, sir.
We did not get any answer yesterday. Wait. Uh, have you unshared? I think I have to reshare again. Okay, so I will quickly give the answer for this question. I hope you are able to see my screen. So it says that 1 gram of microbes is decomposing 1.5 milligram of glucose per day. And then when the glucose concentration is 50 milligram per liter, the reaction rate is half of the maximum rate. So we have to find the rate of substrate degradation when the glucose content is 5 milligram per liter and the microbe concentration is 2 gram per liter. So we know the specific specific substrate utilization rate can also be given as U, that is RSU by X. So REC is the substrate utilization rate and specific substrate utilization is minus REC by X, and RSU we will write it as basically ds by dt. That is how much ds is being conserved, and by the help of Monod's equation, this particular thing can be written as Ks by Ks plus S. Okay, so we can get that minus ds by dt will be equal to ksx, x will go to that side, into ks plus s. So here ks is the half saturation constant, k is the uh, that is the utilization constant, and then s is the substrate concentration. So here k value is given as 1.5 milligram of glucose, that is degraded by per gram of VSS, that is microbes per day. So my K value will be equal to 1.5. K's value means the half saturation constant. So when the reaction rate is half of the maximum rate, so that value of substrate is the K's value. So it will be 15 milligram of glucose per liter. S value we have to find out for 5 milligram of glucose per liter, and X value is also be given as 2 gram per liter, that is 2000 milligram per liter VSS. Okay, so everything is given. So now my minus ds by dt will become 1.5 into 5 into 2000 divided by 15 plus 5, which will be equal to 750 milligram glucose per liter day. So if we see ds by dt, it will be equal to minus 0.75 gram glucose per liter day. So minus signs indicate that my substrate is getting reduced. So simple application of Monod's equation. If you know this particular equation, you have to, all the values are given in the question, you have to just substitute it, you will get the answer. Is it okay, Saket?
Yes, sir.
Okay. Okay, guys, so that's all for today's lecture. So we will meet again in the next Tuesday from 7 o'clock again, and we will discuss about week 8 lectures. And if you have any doubt, you can contact me over mail. I will share my mail ID once again. So this is my mail ID. You can contact me in the same mail ID, and we can solve the problem if you have any. Okay.
Okay. Thank you, sir.
Thank you, sir.
Okay. Thank you, guys. Bye.